Welcome back to The Explainer. Today, we're zooming out to the very edge of theoretical physics, but we're actually starting from a place you probably haven't thought about in years, your high school math class. We are diving into a highly theoretical and totally fascinating paper by independent researcher Dr. Ahmad Riemann. His paper proposes that a basic algebra formula, specifically the difference of cubes, might just hold the key to completely redefining physics and mathematics as we know them. It is a massive, bold claim that bridges elementary math with the very fabric of our universe.
Here is our roadmap for today. We'll start with a simple algebraic identity, then scale that up to volumes, explore exactly why Euclidean space fails us here, introduce the planetary mathematics framework, and finally, look at applications scaling all the way from atoms to strings. Let's just jump right in.
Section 1. A simple algebraic identity.
So this whole paradigm-shifting journey actually kicked off in a recent thread on X. Dr. Riemann pointed out something pretty profound about this classic math law, noting how it clarifies just how massive a difference in volume you get when you tweak a linear measurement by just a tiny bit. It's not just some abstract mathematical quirk, you know? The author is arguing that this actually encodes a foundational reality of our entire universe.
Now think back to this familiar equation. You definitely memorized this for a test at some point, right? But instead of looking at A and B as just abstract letters, I want you to picture them as side lengths. That A minus B part, that's the linear interval or the gap between the two variables. And what the paper shows is that when this linear interval, let's just call it K for now, increases, it blows up the volume difference dramatically. The volume gap between two states isn't just a flat rate, it's completely governed by that quadratic piece on the right side of the equation.
And notice how beautifully this scales up. Step 1. When the interval k is exactly 1, meaning a and b are just consecutive integers, the whole thing simplifies. Right down. The volume gap is exactly that quadratic factor. Step 2, bump that interval to 2, and the result perfectly doubles. And for step 3, if you take any general interval k, the volume gap scales directly and exactly with k. So, when you get to really large numbers, that volume difference just explodes. It's literally the square cube law, but expressed in a perfectly discrete mathematical form.
Which brings us to Section 2, scaling up to volumes. Okay, picture A and B as the side lengths of concentric cubic shells, kind of like a smaller box perfectly nestled inside a slightly larger box. The author explains that our equation perfectly describes the volume gap between those shells. Say you have a shell thickness of 1 centimeter, you get a very specific volume increment. Double that thickness to 2 centimeters, you exactly double that volume increment. So it essentially proves that the discrete algebra we just looked at maps flawlessly onto continuous volume elements in geometry.
But here's the catch. The universe isn't made of cubes, is it? It's made of spheres, planets, atoms, stars. Well, the paper asserts this exact same principle holds true for the three-ball, which is just math shorthand for a solid sphere. For a sphere, the infinitesimal shell's volume, that dV, is just its surface area, 4 pi r squared, multiplied by its thickness, dr. Do you see the structure there? It is a quadratic factor multiplied by a linear increment. It recovers the exact same structure of our initial algebra formula.
All right, moving on to Section 3, why Euclidean space fails.
And this brings us to the core conflict of Dr. Riehann's entire argument. Standard Euclidean space, that flat metric we use for pretty much everything, actually distorts distances, especially out near the boundaries. Why? Because it completely ignores this cubic volume explosion we just talked about. Real physical objects, like planets and atoms, they demand the spherical topology of a closed three-ball manifold. This closed three-ball manifold naturally handles that explosive cubic scaling in a way that flat, linear coordinates simply cannot process.
So, what is the solution? Section 4, the Planetary Mathematics Framework. Under this proposed framework, traditional flat algebra is completely replaced by intrinsic spherical geometry. By utilizing heavy-hitting tools like Stokes' theorem and radial integration, this planetary calculus automatically incorporates the boundaries of real physical bodies. It's literally a system designed to treat objects globally, beautifully converting volume into surface areas multiplied by those quadratic factors. Rather than chopping the universe up into distorted flat patches, it embraces the natural curved geometry of reality.
And finally, Section 5, applications from atoms to strings.
Let's start incredibly small, right at the atomic level. The paper proposes a brand new atomic model where every single atom is itself a miniature closed ball, obeying this exact volume scaling. Because of that cubic volume explosion, a mere 1% radial increase in hydrogen or helium atoms results in a massive 3% volume and energy increase.
And the author states this actually explains observed spectral shifts in our upper atmosphere, totally naturally, without needing any ad hoc adjustments.
But it goes deeper. The author asserts that this spherical calculus even resolves some of the biggest, most stubborn headaches in number theory, specifically the infinities that absolutely plague flat Euclidean space. By naturally supplying the right multiplicative factors, this framework harmonizes incredibly complex mathematical concepts like Zeta regularization and Poisson summation, and it does it without the usual infinite divergences popping up.
And scaling up to the absolute theoretical limit, this framework even claims to reformulate string theory. By placing string theory variants on ball manifolds, the world sheet essentially becomes a two-ball boundary, and the target space becomes a higher dimensional ball. This means that cubic scaling governs the energy of string excitations, which brilliantly yields finite masses and resolves ultraviolet divergences by providing a natural cutoff right at the manifold boundary.
So the really crucial point we leave you with at the end of this explainer is a profound question of scale and perspective. Think about what we just did. We traced a direct line from a simple difference of cubes on a high school chalkboard to the volume of planets, all the way down to the vibration of quantum strings. If an elementary classroom truth is actually the geometric Rosetta Stone that necessitates an entirely new spherical math, what else are we completely overlooking in plain sight? What other basic, everyday formulas are just secretly waiting to rewrite the laws of physics? Something to think about. Keep questioning, keep looking closely at the basics, and we'll see you in the next explainer.